Now, what's tricky about the aldol reaction is that it often doesn't stop at the beta hydroxycarbonyl product. If you heat it even just a little bit above room temperature, another reaction occurs. So it's always good to draw the aldol reaction mechanism and get used to it. So let me pull in this next example, is just a little bit more structurally complex. But of course, the mechanism just starts the same way. This aldehyde has two alpha H's, so we would begin the reaction mechanism by making the enolate. I'm just going to bend my methyl down, the remaining H's here, making the enolate at that alpha carbon. Next up, I bring in the second molecule of aldehyde. This is going to act as a carbonyl acceptor. So from enolate alpha carbon to carbonyl carbon, that joins the enolate part, which I'm bending that methyl down, to the next part of the structure coming from the second aldehyde. All right, and then we would just grab a proton to finish that off. All right, so here's the initial aldol reaction product, beta hydroxycarbonyl. Now the new part is where I still have base, I still have in my product an alpha H that's acidic. The base can come in and grab that alpha H, making a new enolate. So there's the new enolate focused on the alpha carbon. That's resonance stabilized, of course. But now what happens is that, let me put in my alpha label, the lone pair at the alpha carbon can kick the other way towards the OH and shove it off. Okay, when I do that, I get that alpha beta double bond, and I kick out hydroxide. Now, if you had me in the fall, I harped a lot on how hydroxide's not a good leaving group. But in this situation, I'm in a sea of hydroxide, so the hydroxide is joining other hydroxide molecules. But more than that, the product is very stable because the alkene is conjugated with the carbonyl. So that's a driving force for this elimination. Okay, we can't just pluck off other H's on the other side. This is driven by the acidity of the alpha H. So once we remove that alpha H, we have our stabilized enolate, and then the enolate is able to lean towards the OH and shove it off, making a very stable conjugated product.